So hi everyone, my name is Nabeel Seedat. I'm a second-year PhD student at the University of Cambridge. I'm mainly focusing on data-centric AI and tabular data applications, as well as uncertainty quantification. And a big focus is on high-stakes applications like healthcare. Let me take it on. So I'm super excited to be here and talk about our paper, Data IQ, characterizing and auditing your training data in just 2 lines of code. And this package here that I'll be discussing is based on our NeurOps 22 paper with Jonathan Krabbe, Ioana Bika, and Mihaela van der Schaar. So as we all know, machine learning model performance is heavily reliant on the training data that we give it. And for this year, data quality fundamentally matters. I think I'm probably preaching to the choir based on the conference that I'm at. And while we all know this adage that goes, when we feed garbage into machine learning systems, we're very likely to get garbage out. And the focus of this work here is how can we systematically actually audit this garbage and actually clean it up a bit such that we have highly performant machine learning systems that actually generalize when we take it to the real world. And the big part of this here often is how do we actually audit data sets? And auditing data sets right at the moment, and especially at scale, when we have large-scale data sets, is often very hard and very time-consuming, and for the most part, involves a lot of human effort to actually curate and audit data sets. For example, imagine I have this large-scale image data set of millions of images, and I actually want to find these blurry images like you can see on the screen, because I don't want to pass them to my image classification model at training time. How do I do this in an automated manner? Additionally, imagine I have a large language corpus of, for example, say, movie reviews, and I really want to understand, can I find examples from my crowdsourcing where there were actual mislabelings that actually happened in the data, such that we can either correct this issue in the data, or alternatively, just throw that data point away if we have enough samples. And that's what we really fundamentally ask in this paper. Can we help automate auditing? And the answer to this is yes. We introduced Data IQ as a tool to do this, and Data IQ takes a pipelined approach to solving this problem. We systematically characterize your training data into subgroups, and these are characterizing some sort of data set that you might have into easy samples, ambiguous samples, and hard samples, which I'll describe in a little bit. We do this using any machine learning model that you might have, which could be trained in stages, and that we could checkpoint over the training data process. We then leverage these training data checkpoints to analyze the training behavior of individual examples or data points through the training process. And we call this the per example training dynamics, as you can see on the screen, where certain examples might be learned very easily and quite quickly by models. Certain samples, a model actually might struggle and it might oscillate around quite a bit. And there might be certain samples which a model is just never actually going to memorize even correctly. And on the basis of this training dynamic, which you can see in the middle of the screen, we then can characterize our data in terms of the average confidence through training. But the big fundamental push from Data IQ is that we also want to model the aleatoric uncertainty, which measures the inherent uncertainty in the data, irrespective of the machine learning model. And on the basis of this, we can then get our 3 groups of easy, ambiguous, and hard. So let's dive into how that specifically is done. So on the screen here, you see an example of training dynamics, whereas in green, we have easy examples, which you can see the model quickly learns, ambiguous examples in yellow, which we see this large oscillation through model training, where the model is quite uncertain about it, and a hard example in red is an example which the model is just simply not even memorizing in the first place. And on the basis of this training dynamic, we produce what we call a characteristic curve, which I show on the screen right now. So on the y-axis, we compute the average confidence through training. And on the x-axis, we compute this aleatoric uncertainty or this inherent data uncertainty. And I refer you to the paper for the actual computation. What's interesting about this diagram is that every single dot on this plot is actually an individual example or an individual sample within your data set. And we can now use this map or characteristic curve to actually characterize our data. So the first is, how do we get the easy group? So these are samples for which we have low aleatoric uncertainty or low data uncertainty, and the model is quite confident about, and these are easy examples. We then have ambiguous examples, which we have high data uncertainty about, and those examples for which we have low data uncertainty, and yet even in this case, the model can't even memorize it in the first place. These are hard examples. And you might say, now that we've characterized these three groups, what can I actually do with it that's practically beneficial? So in Data IQ, we look at 4 applications, and I refer you to the paper for a bit more in depth of these applications. So the first is robust data characterization. So what we really first show is this aleatoric or data uncertainty provides consistent sample characterization for similar performing models. And this is super relevant because imagine in a company where we have 2 data scientists trying to audit the exact same data set and might be using models with slightly different parameterizations. We ideally want them to draw the same insights about the same data so that they can come to the same conclusions about issues in the data. And we show that this metric of consistency actually enables this setting to be achieved compared to alternative metrics proposed in the literature. We then also show that Data IQ can facilitate principled data collection. And by this, I mean, we show the metrics in Data IQ are first useful and provide utility to guide feature acquisition if we want to improve a data set. We can assign value to different points that we might want to capture from a feature acquisition perspective and say that acquiring certain things actually might be valuable to reduce this uncertainty. Going beyond sample level, we also look at data sets themselves. And imagine we have 2 synthetic data sets produced by generative models, for example, and we want to decide which we actually want to train on. We show in the paper how Data IQ can enable selecting between these 2 such that the model will generalize well when we take it to real data. And finally, and most importantly, this idea of reliable model deployment, because fundamentally, that's what we all are after. We show that Data IQ's groups, these easy, ambiguous, and hard, can help us to guide sculpting, or you can think of pruning of data sets, which lead to more reliable deployed models which generalize better. For example, we might want to throw away some of these hard and ambiguous samples. A nice property additionally to this, beyond better performance, is that curating this high-quality data set also reduces our computational burden as well, because we have a much smaller data set to train on. And finally, this notion of plug and play, Data IQ is really usable with any machine learning model trained iteratively, whether it's a neural net, which you might use on your images and text data, but on your tabular data as well, it really works with something like an XGBoost, which you might use in the tabular setting. But let's take Data IQ to the road and see what it does in action. So Data IQ, firstly, we look at how can it be used to characterize, for example, text data. The easy examples which are automatically surfaced by Data IQ will represent samples, which you can see here, are often quite correct, and we probably do want to actually train the model on because it provides a good level of signal. As you can see, the positive and negative reviews are actually quite spot on. What surfaced in terms of the ambiguous is we actually surfaced linguistic ambiguity in the text, where you see there's a big portion of green positive sentiment as well as some quite red negative, and this really captures this linguistic ambiguity, and we're able to surface this simply through our groups. And finally, the hard group is just simply examples which often are very much mislabeled. You can see examples here where a very negative review in red is by mistake by a human annotator labeled as positive, and the opposite for the one below. So we can really surface these and probably try change them or correct our data sets, or even throw these away, as I mentioned before. But this just provides an automated way to actually surface these examples. We can also characterize, for example, image data. We show that the easy similarly is the examples we want to keep of celebrities in a data set. Ambiguous actually represents these very blurry types of images, and that would be considered ambiguous, and we can surface that automatically, or images with these obscured angles or different vantage points. And similarly to text, hard would be those with mislabeling that we can draw out from our data set in an automated manner. And we show that Data IQ can really help to understand your data better and really help you to construct high quality training data sets in a systematic manner. And lastly, looking at tabular data, because we're a healthcare group, we really looked at studying prostate cancer mortality prediction in the United States, and we found easy examples correspond to the expected types of patients, patients who aren't very severe and who survive, and patients who are quite severe and often have a mortality outcome. This is quite expected. What's interesting for ambiguous is these are patients with similar features but different outcomes, for whom clinicians should actually go collect more features and actually run more diagnostic tests, and we provide this to a tool for clinicians in this way. And for example, hard are then patients with this heterogeneous outcome where we have the opposite effect. Somebody who's very sick has the lucky chance of actually surviving, and we want to actually show these examples and bring them to the fore to a clinician. Now that you've seen what Data IQ can do, how can you use it on your own data? You can easily apply it to any of your existing model training loops with just 2 lines of code and we provide plugins for PyTorch, TensorFlow, and scikit-learn. For example, a PyTorch type of model, you can keep your training loop exactly the same as you'd have it before. You just want to instantiate the data IQ class before your training loop and pass in your data loader. And then during your model training loop, at the end of every epoch, you just need to call data IQ once. And at the end of training, you can access all of the metrics and get these groups that I've shown you. Similarly, for an sklearn model, it's just as easy. You need to instantiate data IQ once, pass in your training data, and post-training, call data IQ one more time to audit your training data set, and we can compute the metrics right at the end. So you can see it's really, really easy to get started with data IQ and apply it on your own data sets to start this auditing process without even fundamentally changing any of your training procedures. The contributions of data IQ is that we can characterize samples in a data set in an automated manner. We highlight the benefits of understanding this inherent data uncertainty, and we provide a very useful tool for practitioners to understand quality of their data, guide feature acquisition, and even sculpt your data set in a better way. And it's very useful for any data modality from image to text to tabular, and with a variety of model types in mind. Please reach out. We'd love for you to engage with Data IQ, take a look at the paper, and take a look at our open source package. We hope that Data IQ can help you improve your data-centric applications as well. Thank you.
Amazing. Thank you, Nabeel. We have a question coming from the audience, which is, how does your solution compare to the similar capabilities of CleanLab?
So I think the very difference between us and CleanLab, and I think CleanLab's a fantastic package, is that CleanLab looks at particularly just mislabeling in one case. But additionally to that, what Data IQ adds is this ambiguous group of, particularly often in a tabular case, of these are examples where you actually have the ability to improve the sample by collecting additional features. And I think that grouping of this ambiguity is like the unique selling point.